this on earlier. So I need to share both screens. I don't know if it's big enough for people. If this looks fine, just say okay.
This is quite wide.
Yeah, I know. They're two basically a wide screen for, but I like to show things on both screens today, so hopefully people can still see the words. Okay, welcome everyone. Thank you for joining. This is our 22nd session at Hackaday Quantum Computing. So 2 weeks ago, we had our first guest lecture. Today we have another guest lecture. I will introduce you, Rolf, in a little bit. Before we go into that, just a reminder that all of the class materials are on Hackaday in the Quantum Computing through Comics course. If you search in hackaday.io, you can find it. And usually we spend 30 minutes to an hour on Sunday on one concept. And it could be theoretical, it could be on hardware or programming. We also have been using the qSharp documentation from Microsoft and quantum katas as our exercises. If you look at some previous classes, you'll find the materials and some classes involve coding. So as I mentioned earlier, we have been, we just started our guest lectures. So last week, we had to change schedule for Professor Chris Furry, but today we are very lucky to have Rolf here, joining from the qSharp community. And we have all these great lineups in the next few weeks. Before I introduce Rolf, I also wanted to remind everyone that we have a lot of learning materials, and I like to show people this community that is building the ecosystem together. So a lot of us in this class are curious hobbyists, but we have a lot of material that's out there that is available for you to upgrade your skills. So I want to point people to the new MS Learn modules. We launched this a while back with 2 modules, and at Microsoft Ignite, we just launched another 2 modules. So now we have a learning path of 4 modules. The first one is to help you get started with coding qSharp, but if you need some quantum concepts, you can also take a module on that. Then we have a more deeper dive algorithm module on Groover search. And then there is also a module on solving optimization problems. This is more theoretical. So I will highly encourage you to go through all of these. And I am very eager to see more people jumping from the curious hobbyists towards the more quantum professionals. So I think Rolf here is a great example of quantum developers and who have been making a lot of contribution professionally to the quantum community. And also I want to thank people for buying my book. The Quantum Computing Comics book now is available on Amazon in 13 markets. The best, actually, people like the drawings, but I think to get the best results actually is to watch the classes of the corresponding topic. And on this side, you can even take notes. That's why I have this notes empty pages for people to take notes while they walk through these topics. So this would be what I think the best way of using the comics book. Okay, so without further ado, let's introduce Rolf Huisman. I hope I pronounced my name right. Okay.
Huisman.
Yeah, thank you.
Doesn't matter. Yeah, doesn't matter.
Welcome to our class at Hackaday on Sunday. Rolf, as I mentioned, has been an active member of the qSharp community. He actually organizes and manages it with Dr. Sarah Kaiser. And the qSharp community is an open source community that's driven by the community for open source projects and contributions to the libraries for qSharp language. And Rolf is similar to a lot of us here. And I would also show the qSharp community website here. I pointed people to it some time ago. Also, he's a hobbyist for a lot of interesting maker stuff, and he has his maker space
at home.
Yeah, and today he is going to introduce to us the project qTril. Is a project that you can run on Microsoft simulators using qSharp. And he's going to show us how we can work with it and how you can do your own programming on simulators, especially with the hardware limitations at the moment. All of the recording will be posted very quickly after the class on both YouTube and Hackaday. And also, yeah, just a reminder, next week, I will be speaking at Zen 4 Maker on Groover's algorithm. So we won't have a class on October 4th. So note the time change. If you want to join that class, you can go to Zen 4 Maker. And then the week after, we have Dr. Maria Schaut talking about quantum machine learning. So a lot to look forward to. Thank you, Rolf. I will give the screen to you now.
Thanks. Let's see if this works. Feed number 2. Can you see the screen?
Yes, very good.
Cool. So hi, everybody. I'm Rolf Huisman. I'm talking for the, like Kitty already introduced, I'm part and one of the maintainers from the qSharp committee. In my daytime job, I'm an enterprise security architect for a multinational bank. So normally I'm not allowed to talk a lot about those kind of things, but in my private life, I live in the Netherlands. I'm Dutch. I'm a dad, and I really like to make and tinker with stuff. And I'm a real big enthusiast of quantum computing. And with all things that you really enjoy and really like to do, when you're only alone, and you don't get together and do things and really get to talk about them. So a while ago, and it's to the 27th of April already, I had to look it up. It's more than a year ago. Together with Dr. Sarah Kaiser, Crazy for Pi, as we nickname her sometimes, we together essentially set up a community for qSharp, the quantum language you already know from Microsoft. And on this site we have, we talk together, we play together, we have opportunities for blog posts, and people usually communicate a lot. And in our open source community, we also have our open source projects in which we collaborate together. So we have two types of projects. The first type is the real qSharp projects that are libraries and things to program for. For example, Sarah, together with Olivia, wrote the QRAM library, which is a library you can use for qSharp to facilitate the possibility of using essentially QRAM for machine learning. Sarah started the Algorithm Zoo, which is a platform of re-implementing a lot of base algorithms everybody knows from the textbook, and show and see how they look in the essentially in the qSharp language. And where I'm mostly focused on, and what we also like to do, is essentially the tooling to make qSharp better and to be able to make better use of it. And the tooling projects we have in that space is the qSharp integrations, the CHP simulator, and qTril, which will be our latest edition, a new project that we're starting for essentially our community. And we invite everybody to essentially have around and tinker around with this. So what do? We have a Slack channel in which we collaborate together, have fun, have chats, and we basically debug and play around together with our fancy qSharp applications and the library. And you can see this, this is a real screenshot from essentially our conversation. Here you see, for example, Amir as well. There are a lot of people which are interested and really want to learn. And once you have a problem, people really want to debug and get into the nitty-gritty. So in our community, we now are starting a new project, and that's Project qTril, and that's what I want to talk about you. What is it? Why do we need it? And why do we even need these kind of things? And to explain what qTril is, that's that ability to plug in multiple simulators into Q#. We also need to talk about our CHP simulator, which is essentially the same, but using a more specific purpose attribution to it. I will show you, once we've talked you through on what it does and how it does, I'm going to show you some demos. And of qTril, that one is a really early POC. We only got that one compiling only a few days, only a day ago. So let's hope that that one works. And this is the first time it will run on Mac. So let's see if it works. And then a call to action. So what is qTril and why would we need that? Well, let's go back to that nice sheet that we are collaborating on some code. This was during the period that we were developing the QRAM library. So this was a very new opportunity where we were looking at, okay, how can you make better use of qubits so that you have the ability to map to other points of data so that you can bring essentially for machine learning your data into your program. And we were running in some small bugs and defects, mostly in the phase algorithms. And then Amir said like, hey, you know what? I'm just going to make a small export of this. Well, this is what that small export looked like. It was 32 of these pages. And yeah, if you have worked with larger programs, like the toy examples, you can still draw out on one screen. This one, even if you have an 8K monitor, I think you still would have to need some additional real estate on your desktop. And we were looking at this and we were trying to debug this. And eventually Olivia came around and he said like, yeah, oh yeah, I just switched around one T gate in this complete stack, and yeah, we fixed it now. But as you can imagine, as if you are writing these kinds of programs, and in reality you are building these kinds of programs, you need a better way of dealing with these. So there are multiple options to deal with this. I mean, we could have really big, powerful quantum computers to run these algorithms. Well, I think someone on the chat line is working on that. You could also have a big simulator with a huge amount of RAM to be able to run these kinds of algorithms, which, yeah, basically for a community is not really feasible. So the path we are looking for and why we are looking into these kind of things is to break essentially pieces of these codes up, pieces of the code up, and to be able to test them individually and run them on specific purpose simulators that are capable of running that specific piece of code, so we can test them in more situations. So how do we do that? Well, the Microsoft QDK stack, which essentially gets shipped if you essentially download the Q# project and you start playing around with it, and a lot of you probably have. They basically have 4 simulators already in the box. There is the real full state simulator, which can handle all the operations, but that one, if you start using more than, for example, 30 qubits, requires so much RAM that you basically can't run it on a normal machine anymore. You need to scale out to, for example, Azure Quantum later on, hosted service for us. But if your problem that you wrote down and basically developed is small enough and only contains, for example, Toffoli gates, X and C nodes in there, you're also able to use the Toffoli simulator from Microsoft. That one can handle a lot more qubits, but the downside of it is it can't handle things like Hadamard gates or phase gates, and it can only measure in the Pauli Z-axis. There are also some other simulators which are special purpose for things like resource estimators and trace simulators, but for if we really are starting to test large applications, when we start to really test algorithms, yeah, you need to be able to focus them out. So these are quite useful. How could you build your own? Well, a while ago, we had a community project called the CHP Simulator. That's a simulator based on CHP subtheory. And that one can do Hadamard, the phase gate, and the CNOT. And because of that combination, also the Pauli X in all axes of the Pauli, in all measures of boundary. This will already allow you to test things like linear error correction, teleportation, dense quantum coding, and the GHZ paradox. And we were really essentially plugging into the quantum language where we can still make use of the quantum, the Q-sharp language as a DSL, but essentially add our own plumbing and tooling in there so that we can, and you will see later on in the demo, can run much bigger programs than you normally would be able to. So this made us wonder. We were developing this, and Sarah developed this online on her Twitch stream. And we wonder, like, how far can we take this? Well, that's where qTril comes in. If you're familiar with the Q-sharp language, the name of Q-sharp, it's a little bit based on the C-sharp name, right? And C-sharp was originally a music symbol, which was C++, and if you add ++ to it, you get a sharp symbol. So what we thought is that what we want is something that is more melodical, like multiple vibrations in the tone of our system, and it needs to be in the same theme. So that's why we called it Thrill, and because every quantum computing language needs a Q in front, we called it qTril. So what do we want? Well, we want to keep Q-sharp as the DSL, as we already said, because that's where the value of Q-sharp is. It allows you to essentially deploy to multiple target systems, and it will allow you to reason in a uniform way about quantum computing. But we want to take out blocks of code and test them individually. Q-sharp allows you to have unit tests, and those unit tests also allow you to specify which specific simulator you want for that specific piece to be tested. And we want to test them with specific noise models, because if you're developing, for example, for real hardware, you would see that you also want to encompass, like, okay, we have these deviations, we have these systems, and test for them with a huge number of qubits. So that boiled us down to, we really need to have an ability to essentially plug in multiple simulators. And what the CHP simulator taught us is that, yeah, given that we already know how to make our own simulator, why don't we hack this together? And that's basically where the project here was. And it's currently in the POC phase. We're currently testing multiple options. And our intent is really to plug in multiple specific quantum simulators. And you know, another option would be that, yeah, there was on Hackaday this quantum computer, and somebody tried to build it himself. Well, nobody would be foolish enough to redo that and try connecting Q-sharp to that. So let's not talk about that one for now. So if you look at qTril and what we are currently working on, and how we see the world is, there are three different types of simulators. You have the incremental simulators, and basically you have your program running and the world starts, and your program essentially interweaves with your simulator. For example, if you execute an Hadamard gate, the Hadamard gate is executed in a simulator, and you essentially go back and forward. The QDK simulators are like this. You also have the stop the world simulators, where you basically have a complete program, you throw it in your simulator, the world stops, it gets executed, you get a result back, and you process out again. And you have the concurrent types, where you hand over the gates, and essentially the simulator runs on the back and starts processing them. Because the QDK is incremental, the current infrastructure that we have is also built for the incremental world. And our current plans are to work around that limitation, essentially, of how those processes work by essentially either having milling the top out of the top of a third-party simulator, and we have done that before, and it works quite well, that we can have existing simulators run in process. Or or for the simulators where we're not able or allowed to do so, we want to build a harness that we can essentially have a stop the world simulator executing individual jobs and process them. So why is this fun? Well, this is really fun because this is uncharted territory. Nobody knows if we're going to plug that in, how everything is going to react and what the end of the possibilities are about this. We're currently in the design and prototyping phase, right? And that also means that we're currently validating if this works, and we think it does. The prototypes and the prototype are going to show you hopefully works, and I will be able to show you that the concept works, but we're really in looking at like, okay, how would we do this the best way? How can we integrate that? If you really like these kind of things, well, we're going to send out a deck. Join us. This is really fun material to talk about. So let's talk a bit on how technically we are going to do this. And for that, I'm going to give you some inspiration. And what was our inspiration for our qTril simulator, which was the CHP simulator. So the CHP simulator, and Sarah started this one, is based on the stabilizers theorem of Gotsman from 1996. It can handle Hadamard, phase, and CNOT, and therefore within that space also the Pauli exclusion in all axes. And you can find it in the bottom link if you really want to see how it technically works. So if you look at these gates, because people will usually ask why these gates. If you look at these gates, you would see that the Hadamard has the ability to go from the 0 state to the plus state, from the 1 state to the minus state. The phase state can bring from 0 to 0, from 1 to I, and etc., etc. None of these gates, essentially, and that's also why they're called Clifford gates, can bring you to essentially all the substates of the block sphere. And that's an opportunity where we can make use of. So for example, where you probably have seen this block sphere where every point on the block sphere is a possible state in your application, in the CHP set, you only have 6 states from one qubit. And that will allows us to massively compress the states that we use using here we go, using Pauli matrix multiplication. So what we do is we use group theory. And if you want to know it in much more detail, there is the paper from Arons and Gotsman. But basically what this allows us is to simulate this specific set in a very efficient way on a classical computer, as long as we keep to these gates. Well, okay, that's the theory of a CHP simulator. How do we connect it up to the Q# language? Well, there are basically 3 ways of connecting a program up to the Q# language. You can build and plug in your own simulator. And that's basically how our qTril, how a CHP simulator works and how our qTril proof of concept currently works. Other options would have been the custom compiler extension. So if you really want to rewrite code and do all the other stuff, Q# has the ability to do those kind of things. Another option, and it came out on Wednesday, that's the QIR, or Quantum Intermediate Representation, which is basically the MSIL language for quantum computers later on. And we are currently looking at if we can make it work, use it, but that will probably be our focus for qTril later on. So let's go back to the CHP simulator. How do you build your custom simulator? Well, first, let's discuss on how a Q# is normally executed. You normally have a Q# program, and it has its host program, which is technically optional, but under the hood you always have that. And it executes the Q# programs. And it executes the programs against either a quantum device, which they call a target machine, or basically the simulators. And the way this technically works, and you can plug and play this without changing the Q# code, is that if you have, for example, the program on the left, and this is within Visual Studio Code, a lot of you might use more the Jupyter notebooks for this. So this is the code representation as you would see it in a development studio environment, where you have an application with A and B, and you have the Hadamard gate executed, the CNOT gate executed, etc., etc., etc. For all of these steps, in the simulator, and this is a class depending which extends the quantum processor base, all the methods are called for all these gates. So for example, the Hadamard gate, the H function is called. For the CNOT gate, the CNOT function is called. And by implementing your own version of these, you can build up essentially your own simulator. So if you do that correctly, and this is an export of what that looks like. On the top, you see the left program using the traditional full state quantum simulator, which uses matrix multiplications to essentially execute the program. You see that the end result on the bottom is 0, 0, as you would expect. And on the bottom side, you see that with the .NET command lines, you can plug in our own simulator, which does the same, which does all the interesting stuff with the matrices and all the other stuff, and also executes the same. Well, and it also executes with the same 0, 0. So that way we basically don't change the program, but we can plug in different simulators. So let's show that in real life. So what program am I going to use for the Q# and for these demos? Well, Sarah is currently working on the algorithm zoo, and one of the algorithms zoo applications she implemented is the Bernstein Fazirani. Probably going to butcher that name, sorry. So this class essentially is implementing as a community all of the algorithms that are on the Quantum Algorithm Zoo page. And we're going to implement them one by one, and we'll add them as public contributions so everybody can see and have a crack at them. So if I take that algorithm, and this is the Q# version on my laptop in Visual Studio Code, because I'm more of a developer person, so I like this kind of infrastructure. What you see is the Bernstein, let's call it Bernstein for now, algorithm, where you have been given an oracle, and that oracle function has a hidden value. And what the algorithm does is basically by querying, it tries to determine what value is in that oracle function. And normal on a classical computer, you would get a list and you would need to execute all kinds of combinations. But for a quantum computer using superposition, we can just basically query them all and have out what the oracle function is. So let's test this algorithm on a classical computer. Is this screen big enough for people or not? No?
Yeah.
Yeah.
Can see that.
Okay.
There are some questions in the chat. We can get to it. I don't know if you want to.
Oh, sure. Go ahead. I can't see the query screen. So if you can tell me.
Yeah, there's two questions from Sumit. One is, was the quantum class in C#?
The simulators are the simulator extensions as we wrote them are in C#, yes.
And then the second question, oh yeah, it's the same. So they're asking if it's in stabilizer processor.
Yeah, the stabilizer processor is the, I have them here. The stabilizer processor is basically the component which plugs in the runtime, essentially. That one gets called for all the gates. And this code is public on the GitHub page, by the way, if people want to review and see this. So this is my application, and I'm now going to run the application on the traditional simulator. So this is the quantum simulator. .NET Run, the project sample, quantum simulator. I put it a secret. That's just the secret I'm going to put in the article I'm going to query. And then I'm going to execute this with 16 qubits. Sarah is also providing the links. Thank you, Sarah. So this is running on my machine, and what you see is that it executes and I get the same results back. So this, so what we build is the simulator, the CHP stabilization simulator. Oh, that's a little bit too much for now. And what you see is I can execute the same program, and it will give me the same results, hopefully. Yes, it still gives me the same results back. So how does this work with the simulator? So what we have, and it's how you can plug this in, is we have a process simulator which extends from quantum processor dispatcher, which basically creates a custom class which will be hooked up into the runtime. And you can specify this class, and that's the name of which you specify with the simulator tag. Oh, do you want the text bigger? Oh, sorry. Which you can, which essentially creates and hooks in the real simulator that you want to execute. And the real execute simulator is in stabilizer processor, and basically that one contains the override methods from the processor quantum processor base, which are the components which get executed. If you go even deeper, you will see all the plumbing and definitions and how we implemented the rest. But basically, this is how the glue of the qsharp language and the our custom simulator interact together. And you can play and you go on and on and on, back and forward. So this is nice, but if I already have a simulator from Microsoft, why should I implement this? Well, the problem comes once you start getting into this territory. The qsharp also compiles to IL. It's a little bit more complex than that. This qsharp program gets parsed, and if you look in the object directory, you can see the components at which it's got implemented to. Sorry, this one. It gets on the back. It gets compiled to this C# file, which basically calls back the simulator. And this is compiled into the DLL. And that is an IAL for now, but if in the future, for example, if you have a target machine, you would have other stuff poking in here. So today, yes, today it compiles to IAL. So going back, if I have my quantum project, and suppose this application would be a lot bigger, and I now want to simulate this with 60 qubits. So, okay, I'll execute this with 60 qubits using the traditional simulator. And nothing happens. It's silent. I can't do anything. And if you look at my process statistics, you would see that the .NET runtime will grow. Well, it's currently at 5 gigabytes. It will eventually stop at 16 because there's only 16 gigabytes in this machine. And then it will die like, hey, I'm out of memory. I can't simulate that many qubits. So this won't work for these kind of programs. Well, okay, let's try the other one. Let's do this one with 60 qubits. Oh, here's the result. Does this mean that the full state simulator is bad? No, definitely not. This simulator is specifically purposed for these kinds of simulations, which only make use of the Hadamard gate, the Hadamard gate, the Pauli exclusion gate in the x-axis, and essentially the phase and the CNOT. And that's why this is able to, essentially for those specific use cases, if you plug it in, you're able to simulate much bigger quantum computing devices. You can even, and I will show you this, by default, we fill it with 1024 qubits. Yeah, just because we can in the simulator. So even if you have really big programs, and if you don't just have these If you just use these gates, yeah, you can still run them. Okay, so that's nice. So how does so this is how you can plug in your own telemetry, and how you can essentially plug in your own simulators this way. So what does this look for qTril? Well, in the case of qTril, and this is a very early prototype, I have here a very in C, some from a research paper. I got a version of a simulator by Scott Aronson himself, who wrote a simulator in C to just execute these kind of things. And this is in hard-coded C. It compiles to a real native program. Can't run it. Okay, so how do I plug this then in? And that's basically where our first prototype is essentially capable of doing. So by switching that one around, and now I need to do this switcheroo. And I really hope this one works. This is sample. This is the qTril simulator. Bum, 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 bum. Did we break? Yes, we break. That's the nice thing about beta applications. Need to recompile, sorry. We can, but what you're seeing is that we're switching around simulators on the fly, and this will be as easy as switching machines later on as well. This really proves that the Q# language is really a language that is not dependent on what kind of hardware or simulator is below that, and essentially a DSL, which will allow you to reuse this later on as well. Okay, attempt number 2. Off. So what you see now is that I switched out the simulator, and it's now using the research paper simulator from Scott Aronson, and I'm using this in the Q# language. Notice I didn't change anything. I just plugged it in and it works. And this is our intention, to go even beyond this, to have more ability, and I get the correct result, which is not unimportant. So I now have the ability to plug in all kinds of simulators, and what we want is to even have more types of simulators, so we can really focus the sets that we want to test on. So let me get back to my deck. So this is one of the projects that you see on the GitHub page that we are currently working on. But there are much more fun things that we have as well. So like I said, we have the algorithm zoo, and we also are working on quantum. We also worked on the quantum RAM and quantum ROM memory libraries to execute on those. And these are really fun things to do. And don't do those things alone. Do those things together. It's much more fun. Because if you're alone, you're just alone. So come join us if you don't want to be left behind. Are there some questions?
Bravo, thank you.
Thank you.
And for people just, if you're confused by C#, why there's C# and how is it related to Q#, you can go through the MS Learn module. It walks you through some of the concepts, and the documentation by Microsoft Quantum also explains it. Also, if you want to try hands-on, the MS Learn modules teaches you how to use the resource estimator and simulator as well. So step-by-step walkthrough if you are confused by any of those. Yeah, there's some questions in the chat if you want to take a look, Rolf.
Yeah, let me switch to the... Normally when I'm on Windows, I have multiple screens, but now I just have 2. Let me check. Oh, Sarah is also answering a lot of them already.
Thank you, Sarah.
Yeah, and that really emphasizes this is not something we want to do alone. This is something we do together with a group. Also with Amir and Olivia, and there are a lot of people. That makes it a community. You're not alone. You're not alone. It's really fun to do stuff.
Yeah, and we need the community for anything new that we introduce to the world.
I think Sarah answered them all. So thank you, Sarah. High five.
Although the recording would not get the messages, so.
Oh, then I'll.
I can possibly just copy. Yeah, I can copy and paste the question and answers in the Hackaday into the Hackaday project page, so people can see that too.
Okay, that one was answered. Please make the text bigger. We did that. Do you gonna code in C# or Q# DSL? Okay, that was a question for Sarah. And Sarah does both. Let's check. Did she say that? Yes. The algorithms we will be implementing on the algorithms, so those will be in Q#. Most of the tooling, because you're talking to the infrastructure, that's mostly in C#. And probably later, once we really have Queer, we'll probably have some C++ and C in there as well, because that requires it a bit. I would have liked to demo that, but that doesn't work at Mac today. So that's why I needed my Windows machine.
People can join the Q# community and also join the Slack channel, and you can collaborate that way, right?
Yeah, you can connect up and
GitHub open source. There is a question about Azure, if it's already offering any type of Q# services. The answer is yes. On Azure Quantum, we've already built Q# applications and case studies with our customers, and quantum-inspired optimizations with partners and customers. And the answer is there will be more.
So anything, what is MS plan for QRAM? I can't answer that because I don't know.
Yeah, I don't know.
Like I said, Sarah and me, we are MVPs. That means that we're not part of Microsoft, but for our contributions, we have been acknowledged. So we don't know.
Yeah, and also, like a lot of things the community is built is not owned by the company. It's free and it's open source and anyone can use. So just Quantum will be the same. So yeah, and it's the tool that the company develop something, but then community drive it forward.
Yeah, and we like it and we play along. We play a lot with that. And sometimes we we just have fun with it.
Yes. Sarah posted the link to our Ignite talk for Azure Quantum. That's also a good place. Cool. Is there any other question Rolf can answer here? Yeah, good.
How is data acquisition from a data point? I'm very curious what he means with that. Could you please elaborate what your question is? Like, for example, a homebrew quantum computer. Let's put it like this. It's quite difficult to build your homebrew quantum computer. I know from experience. But there was a talk on the Chaos Computing Club of 2019 about someone who tried to build a trapped ion device. So for inspiration, you might look there.
Cool. I think the time is good. Thank you so much again, Rolf, for joining us, and thank you, Sarah, for monitoring. We have a great community here, so please take a note at all these links and join the quantum developers.
And if people have specific questions, they can always try to contact me at the contact address.
Yeah, we'd love to see more contributions for quantum as a field from all the community members here. Thank you.
So thank you. Hey, thank you, Kitty, for inviting me.
Yeah, thank you so much. This is a great session. We should do more.
Thank you. Talk to you later.
Yeah. Have a
Yeah,
good
bye-bye.
rest of the day. Bye.